Good day to everyone. So we'll be discussing part 3 of module 4 for the subject CE3151. And the topic is Gauss-Jordan elimination. So the second method under row reduction is what we call the Gauss-Jordan elimination. So whenever a system cannot be solved simply by the Gaussian elimination, we may now apply the Gauss-Jordan elimination, as it is simply defined as a continuation of the Gaussian method. So in here, the row echelon form that we have achieved from the Gaussian elimination is turned into a reduced row echelon form, or better known as an RREF. So the augmented matrix that we have derived will now be turned into a reduced row echelon form, wherein we'll now have an identity matrix for the variables or the coefficients representing each of our variables. So basically, in reduced row echelon form, the main diagonal will have values equivalent to 1, and the elements found below and above the main diagonal will be equivalent to 0. So for the steps for Gauss-Jordan elimination, we'll have basically, first is to make our element A11 as equal to 1. Remaining elements for the first column will be equal to 0. Thirdly, your second element in the diagonal is turned into 1. Remaining elements in the second column is set to 0. Fifth step is to set our diagonal element to 1. And then lastly, for the remaining elements in our third row, we'll now be setting that to 0 again. And then if we have more rows and columns in our matrix, we just simply follow the general format wherein the main diagonals are all equivalent to 1 and the elements below and above our main diagonal are all equivalent to 0. Okay, so to understand the relation between the Gauss-Jordan elimination and the Gaussian method, let us try to continue solving the system in our first example of Gaussian elimination. So from our previous discussion, we were able now to get the row echelon form of the given equations or of the system. So in Gauss-Jordan, what we want is that all of the elements in the diagonal and the elements in the column of the constants will all be non-zero. So meaning all other elements will be equal to 0. So for this problem, we now continue to solving now or setting the remaining element in column 2 to 0. And we can achieve that by multiplying -2 to the values of R1 plus the values of the elements in row 1. So that will now be -2 times R2 plus 1 or R1. So we move to the next column, -2 times R2 plus R1, -2 times R2 plus R1, and -2 times R2 plus R1 is now, so we'll now have another matrix which is simplified. And then next, we move on to the last column. So the remaining elements in the third column will now be set to 0. So let's start off first with the first row. And we can achieve that by multiplying now R3 by 7, adding up the elements of row 1. So we'll have now 7 times R3 plus row 1, 7 times R3 plus R1, 7 times R3 plus row 1, 0. Then 7 times R3 plus row 1, this one. And then lastly, we have the last element in our RREF to be reduced to 0. So we can achieve that by multiplying negative 5 times R3 plus R2. So that will now be negative 5 times this value plus R2, negative 5 times R3 plus R2, negative 5 times R3 plus R2, negative 5 times R3 plus R2, this matrix. So this one now is our product from Gauss-Jordan elimination, or this is now our row or our reduced row echelon form. And from this matrix, we'll now be able to identify that x is equal to negative 1, y is equal to 1, and z is equal to 1. So basically, if we continue now solving for all of our diagonals equal to 1 and all other elements are equal to 0, then we will be arriving directly at the values of x, y, z. Unlike what we did in Gaussian elimination, we were given equations and we derive the values of the other variables based on our equation or the value of one variable that we were able to identify. Okay, so if we're going to check from our previous discussion, we were also able to solve for the values of x, y, z as negative 1, 1, and 1. So using Gaussian elimination and Gauss-Jordan will still give us the same values of your variables. Then, aside from that, the values of x, y, z may also be written in matrix form as matrix of x, y, z is equal to negative 1, 1, and 1. Okay, so next example, let's try continuing our example 2 from Gaussian elimination. So we were able to get your row echelon form. So next step is to reduce the remaining elements to 0. So we'll now have to multiply 2 to R2 plus R1 to simplify negative 2 here. So we'll now arrive at 1, 0, 9, 19. So if you apply this one, so that's 2 times 0 plus 1 is 1, 2 times 1 plus negative 2 is 0, 2 times 3 plus 3 is 9, 2 times 5 plus 9 is 19. Okay, next we reduce 9 to 0, and we can achieve that by multiplying negative 9 to R3 plus R1. So that will now be negative 3 times, or negative 9 times 1 plus 9, we get 0. So negative 9 times 1 plus 19, we get 10. And then lastly, we simplify 3 in the third column to 0. So we'll now achieve that by multiplying negative 3 to R3 plus R2. So we'll have 0, 1. Then we'll have negative 3 times R3 plus 3 is equal to 0. And then the remaining is negative 3 times 1 plus 5 is 2. Or this now is written as x is equal to 10, y is equal to 2, z is equal to 1. So if we're going to check again, we also have the same values for x, y, and z with our Gaussian elimination process. So let's solve this another example for Gauss-Jordan elimination. So we have here a set of equations. So we have your linear system. So let's transform this to our augment matrix form. So this will now be 3, 2, 4, negative 2, 1, negative 3, 2, 20, 0, 1, 3, 2. So we want to have our A11 equal to 1. So we could simply reduce this to 1, or we could apply swapping or interchanging of positions. So what I will do is to select for A11 the smallest value in our matrix. So I will now have 2, 1, 23. The second row becomes the first row. And then I will have the first row becoming the third row. So since this is not yet equal to 1, what we can do is to divide the entire first row by 2. So we'll now achieve 1, 1 half, 10, and 3 halves. And then next step is to change the remaining elements in the first column to 0. And we can do that by multiplying now R1 to negative 3, or that's A to 1, plus all the values of the second row. So we'll have now R1 times 3 plus 3 is equal to 0. R1 times negative 3 plus R2 is negative 7 halves. R1 times A21 plus R2. R1 times negative A21 plus R2. This is now our reduced form. Next, for the last component or last coefficient of x, we could now simplify this using the equation R1 times A31 plus R3. So that will now be R1 times negative value of A31 plus R3, 0. R1 times negative 31 plus R3 is negative 5. R1 times negative A31 plus R3. And then lastly, R1 times negative A31 plus R3 is this one. So we have already eliminated all the values for the x's or your first column. So this was our simplified matrix eliminating x. So next step is to make our second diagonal to 1 by simply multiplying the whole of row 2 to the reciprocal of your A22. So that's 2 or negative 2 over 7 times 0. 0, negative 7 over 2 times negative 2 over 7. Next, we have negative 28 times negative 2 over 7. And lastly, we have negative 7 over 2 times negative 2 over 7. So that's 1. And the next step is to eliminate all of our y values. Okay. So we'll have now for 1 half, that is now computed as R2 times negative of A12 plus the elements equivalent to R1. And then for the third row, to eliminate this or make this a 0, that will now be R2 times the negative value of this element plus the equivalent elements in row 3. So we'll now arrive at 1, 0, 6, and 1. Then for this value, we'll have now 0, 0, 0, 1. So if you're going to notice, this value now is 0. 0 is not equal to 1. Therefore, the system has no solution, or the system is an inconsistent system. Okay, so let's solve another example for the Gauss-Jordan elimination. So given now the linear system of 3 equations, 4 unknowns, we first write this into our augment matrix form. So we'll now have this matrix. Okay, so it's arranged as X, Y, Z, W in your constants. So with that, we set now our A11 equal to 1. Since it's already set, we can now swap rows so that we'll have the smaller value next to our basis of our solution. So I'll be swapping rows 2 and 3. So we'll now arrive at this new matrix form. So we'll have now the first element is 1. So elements below it will now be equivalent to 0. And we can do that by eliminating now the values of the coefficients of the x's. So for that, we can now solve it by, for the second row, using the equation R1 times negative of A21 plus R2. So we'll now arrive at 1 times 1 plus 1 is 0. Next, we have 3. So R1 times 1 plus 4 will have 0. Next, negative 1 times 1 plus 5, we get 6. We get 3 times negative 1 plus 4, that's 1. Then for the third row, we'll now be using the equation R1 times A31 plus R3. So that will now be 0, negative 2, negative 7, 2, and negative 2. So for our next step, second diagonal should be equal to 1. So it's already 1. So what we do is to set the remaining elements for y equal to 0, or we eliminate the coefficients of y. And we could achieve that by, for the first row, multiplying R2 times A12 negative plus R1. So we'll now arrive at R2, so R2 times negative 2 plus 1, 0 is 1, R2 times negative A12 plus R1 is 0, R2 times A12 plus R1 is 4, R2 A12 plus R1. And then lastly, we have 1 times negative 2 plus 3 is 1. And then for the third column, that will now be computed as R2 times A32 plus R3. So we'll now have R2 times A32 plus R3, R2 A32 plus R3, R2 A32 R3, R2 A32 R3, R2, E32, R3. So we have now this one. We now eliminate all our, or simplify first the third diagonal, which is -7, and then eliminate all other values of z, or reduce it to 0. So what will we do is to divide row 3 by the value of A33. So we'll have 1. So we'll now arrive at, so this is already 0, 0. We have -7 divided by -7, that's 1, -2, and 0. And then next, we move on to R, or row 1. So that will be R3, this R3, times A13 plus R1. So we'll now arrive at 1, 0, 0, -5, 1. And then for the second row, that will now be R3 times A23 plus R2, or that's equal now to 0, 1, 0, 6, 1, or still the same. So we have already achieved 1, 1, 1 for all the diagonals. So what we can do is that we can write now all our values in the form of x plus y plus z plus w equal to b. So for the first equation, that's written as x minus 5w equal to 1. Then we'll have second equation will be simplified to y plus 6w equal to 1. Third equation is simplified to z minus 2w equal to 0. So in this case, we can simplify that z is now equal to 2w, or we could simplify again, w will be a free variable or a constant, meaning even if we remove w, it will not affect our equation. So simplifying this will now arrive at a simpler form and matrix form of the values of x, y, z, w is equal to 1, 1, 0, 0, or free, plus c times 5, -6, 2, and 1. Or since c is also the same as w. So pag sinimplify ko yan, w is equal to c. 0 plus c. Pag z naman, ibig niyang sabihin is equal to 0 plus 2c, but c is equal to w, so ito din lang yung lalabas na equation ninyo. So that's for Gauss-Jordan elimination. So let's solve again another example for Gauss-Jordan elimination. So given the linear system, let us solve for the possible solution and values of the variables for the 4 equations for unknowns. So firstly, we have to convert first our equation into its augmented matrix form. So we'll have for the first equation 1, -2, -3, 4, -5, 2, -3, 1, 3, 2. Then for the third equation, we have -3, 1, -2, 1, 3. And for the fourth equation, we have 1, 2, -2, -1, and 4. So in Gauss-Jordan elimination, what we want to do is to first make our first element equal to 1. And since our augmented matrix is already starting with element E11 equal to 1. So what we will do now is to simplify again our augmented matrix by eliminating the remaining elements in the first column, or for our column A. So now have these elements to be reduced to 0. And we can do that by identifying first our equation for our simplification. Okay, so for our equation for row 2, that will now be 2r1 minus r2, and then for row 3, that will be 3r1 plus r3, and for row 4, that will be r1 minus r4. So applying now these equations in our matrix, will now arrive with the following. So for the second row, that will now be equivalent to 0. Then we have -1, -7, 5, and we have -12. Then for the third row, applying 3r1 plus r3 will now arrive at 0, -5, -11, 13, and -12. And lastly, for the fourth row, that's r1 minus r4, so we'll have 0, -4, -1, 5, and -9. So we have already reduced our first column. So we move to the next step. So after solving our reduced matrix for So the next column that we want to reduce will be the third column. And with that, we'll be reducing our third element on the diagonal to be again equal to 1. And we'll arrive there by using the equation. So for R3, that will now be all the elements of R3 will be divided by our third element. It's 24. So we'll now arrive for the third row. We have the value 0, 0, 1, negative 0.5, and we'll have positive 2. So next step, we reduce the remaining elements in the third row or in the third column to 0, and we'll now be applying the following equations. So for row 1, we'll have R1 minus 11R3 and then for row 2, that will now be equivalent to R2 minus 7R3, and then for the fourth row, we'll have R4 minus 27R3. So for our equation, we'll now arrive at, for the first row, so notice if we apply these equations, we'll also retain the reduced columns that we have just performed. So for this element, this will now be equivalent to 0. So next, we have negative 0.5. Then we have negative 3. For the second row, we'll have 0, and then negative 1.5. This one is negative 2. And then for the fourth row, that will now be equivalent to 0, negative 1.5, and negative 15. So the last column will be eliminated as well, or reduced as well. So what we'll do is to reduce again the element found on our diagonal equal to 1. And we can achieve that again by solving for the equation, or applying the equation, which is now equal to R4 divided by negative 1.5. So again, I'll be only applying this equation to our remaining values. So to check if our equation is correct, you can always apply it in the other values here. So supposedly, dapat 0 pa rin yung lalabas dito sa ating 3 columns for the last row. Okay? So in that case, for our last element, we'll now have negative 1.5 divided by negative 1.5 is now equal to 1. And negative 15 divided by negative 1.5 is now equal to 10. So next step is to reduce now the remaining elements of our fourth column to 0, and we'll now arrive there using the following equations. So for the first row, we'll have now 0.5 R4 plus R1. Then we have 1.5 R2 plus or R4 plus R2. Then we have 0.5 R4 plus R3. So applying now these three equations to each row will now arrive at 0, 0, 0. And then for our constants, that will now be equivalent to 2, 13, and 7. So in this case, the values of our A, B, C, D now are derived or are computed with this constant. So we could write now the values of each of our variables as have A is now equal to 2, B is equal to 13, C is equal to 7, and lastly D is equal to 10. So these are all the values of our variables. So we're able to solve for their equivalent values. So in matrix form, we could also write this as the values of the variables A, B, C, D is now equal to 2, 13, 7, and 10. So take note that if we use any other steps or methods, we'll arrive at the same, or we should arrive at the same value. So in here, in our first solution, for example 5, we directly reduced our first column to its 0 values. So another solution is that you can interchange the rows in your solution. So I'll be showing again another solution for example number 5, so that we could see what is now the difference, or will there be a difference in our answer. Okay, so for solution number 2, so another way to solve this is what we do first is, again, we put first our augmented matrix form. Okay, and then since our first element is 1, so before we could start reducing, what I will do is to swap now or interchange row 1 and row 2 and row 4. Okay, so we swap R4 and R2 para yung 1 nandun siya sa taas, sa baba lang ng leading element natin. So in that case, we'll now have our new matrix, which is now equal to 1, negative 2, negative 3, 4. That's 1, 2, negative 2, negative 1. So row 3 still the same, negative 3, 1, negative 2, 1. And the last row will now be row 2. So 2, negative 3, 1, 3. And then for our constants, we have negative 5, we have 4, 3, and then 2. Okay. So once we have swap or interchange our two columns, what we do now is to eliminate our equations or our elements under column 1. So for this will now be simply, then write this as, reduce this as R1 minus R2. Okay. Then we have for the third row that can be equivalent to 3 R1 plus R3. Then we have for row 4 that is now 2 R1 negative 2 R1 plus R4. So with that, we could reduce this now into a new reduced matrix. So we'll have negative 5, this one's 0, 0, this is negative 4, negative 1, 5, and this one is negative 9. For the third row, that will now be 0, negative 5, negative 11, 13, and we have here negative 12. And then we have 0, negative 1, negative 7, and then we have 5 and negative 12. So next we reduce the second column. So we first equate this to 1, and the remaining will now be reduced to 0. So in that case, we now reduce this by dividing now R2 by negative 4. So we'll arrive at this one equal to 0. That's 1. 1/4. And then we have 5 over 4. And then this one is 9 over 4. So next, for the first row, this can be computed now by 2 R2 plus R1. So take note, we are going to use now these values. Okay? So for the third row, we'll now be using the equation 5 R2 plus R3. And then for the fourth row, that will now be equivalent to R2 plus R4. So in this case, we'll now have the following values for our matrix. So for the first row, we have 1, 0, it's 5 over 2, and that is negative Then we have 3 halves and negative 1 half. And then for third row, we have 0, 0, negative 39 over 4. It's 27 over 4. Take note, this should be negative. So next, we have negative 3 over 4. And then for the fourth row, that is now 0, 0, negative 27 over 4. Then that's 15 over 4. And lastly, we have negative 39 over 4. Okay, so we have reduced our second column. Next is we reduce our third column. So what we do first is to reduce this to 1. And then next we reduce the other elements to 0. So for the third element in the diagonal, that will now be reduced simply by multiplying all these values to negative 4 over 39. And then for this row, we'll now have equal to, that's 5 over 2 of R3 plus R1. This would be plus R2. This would be plus R4. Okay. This one is R3. R3. That will be 1/4. Let's put negative there. And then this one is 27 over 4. So I hope you can see already a pattern on how we can solve or identify our equations in our reduction. Okay, so using now these equations, let us now simplify our equation or our matrix. So we'll have now, here is 0, and then we get negative 3 over 13. This is also 0. That's negative 14 over 13. This one is 1. That's negative 9 divided by 13. This one is 0. This is negative 12 over 13. Then for our constants, we have negative 4 divided by 13, 29 over 13, 1 over 13, and have negative 120 divided by 13. So this is now our simplified equations. So next, we now simplify or reduce the last column by reducing this element to 1 and the remaining elements to 0. And we're able to do that by multiplying this to negative 13 over 12. And then this one is multiplying now our highlighted value, negative 3 over 13. there is the negative sign, times R 4 highlighted. It's negative opposite sign, so that's 14 over 13 or 4. That's positive 9 over 13 or 4. So that's plus, this is R1, R2, R3. So with our equations, we'll now have 0, 0, 0, 1. And for our constants, we'll have 2, 13, 7, and 10. Or, writing this now, we now have our final answer as A is equal to 2, B is equal to 13, C is equal to 7, and D is equal to 10. Okay, so again, you can write this in matrix form. We'll have now A, B, C, D is equal to 2, 13, 7, and 10. So if we're going to compare that with our solution, last time, it is the same.